I'm on slightly dodgy ground here because I'm going to do a video on maths, which is not my strongest subject, but as electricians we need to know some basics, and those who are retraining, might have been years since you've done some maths. Let's have a look at some electrical formulas and how the transposition of certain formulas has its practical uses. A good example being the resistance formula. We can transpose this to get the cross-sectional area of a cable. Let's have a go. So an equation tells us that two quantities are equal. The equal sign doesn't mean and the answer is. What it means is this side is equal to this side. So here 4 plus b equals 6. Quite a simple one. Answer is going to be 2, isn't it? 4 plus 2 equals 6. But we could move this formula around. 2 equals 6 minus 4. 4 equals 6 minus 2. That's the point of transposition. We can move around the numbers and letters to find an unknown quantity or value or size. And we have our operations: plus, minus, division, square and square root, and multiplication. A plus will cancel a minus will cancel a plus. A division will cancel a multiplication, and a multiplication will cancel a division. And a square will cancel a square root, and a square root will cancel a square. The square of 10 is 100. The square root of 10 squared is 10. It cancels it out. The really big rule though is when you're transposing, what you do to one side of the equal sign, you've got to do to the other side. I've got plenty of examples coming up. Another basic rule is known as BODMAS, or it could be BODMAS. It's an acronym to help you to remember the order of mathematical operations. It stands for brackets, orders or indices, division, multiplication, addition, and subtraction. So you would work out the brackets first, then you would do the orders or indices, then you would work out division or multiplication, and then you would work out addition or subtraction. So in the first example, 4 plus 7 in brackets, and that's times by 5. And that's the way you would work it out. It's not 5 times 4 plus 7. That would equal 27. It's 4 plus 7 times 5. 4 plus 7 is 11. Times by 5 is 55. 55 is the correct answer. And orders as well. We do the square first. We square the 3, which is 9. And 5 times 9 is 45. That's the correct answer. It is not 5 times 3 squared. 5 times 3 is 15. 15 squared would be 225. So you can see the order in which you do the sums becomes quite critical, because you can get vastly wrong answers. Division and multiplication you can do as read, from left to right. 6 divided by 2 times 8 divided by 3. 6 divided by 2 is 3. 3 times 8 is 24, and 24 divided by 3 is 8. The answer is 8. You can see in the order of operations that multiplication comes before addition. Here's why. In this example here, 5 plus 4 times 6, 5 plus 4 is 9, times 6 is 54. That's a wrong answer. You do your multiplication first. So 4 times 6 equals 24. Then you add the 5 and you get the correct answer 29. Put these into your calculator, you'll get the answer 29. And with addition and subtraction, it's as read as well. 5 plus 2 is 7, minus 4 is 3, plus 8 is 11, minus 3 is 8. You just do it left to right as you see it. I'm just covering the real simple basics here. Things will get a bit harder. So here's our lovely formula wheel. And it gives us various different ways for calculating power, voltage, current and resistance. But there's quite a lot to remember there. But if we know two basic formulas, we can work out all the rest. We have our Ohm's law triangle, VIR, voltage, current and resistance. And we have our power triangle, power, current and voltage. And from these two triangles, we can get every formula in that wheel. Let's have a quick look at some basic transposition rules. We've got our formula here, A plus B equals C. We want to know what B is, so we need to get B by itself. So to do that, as you can see here, we can move the A to the other side of the equal sign. So we need to get rid of this A, so we'll add a minus A, and what we do to one side of the equation we have to do to the other, so we'll add minus A to the other side. A minus A cancels out, and it leaves us with the formula B equals C minus A. Or you can swap it round to C minus A equals B, depending which way you like to look at it. You can always put the numbers in to check your formulas. The more you do it, the more confident you get. You don't necessarily have to put the numbers in. But here in this very simple example, we had A plus B equals C, didn't we? And so in this formula, 4 plus 6 equals 10. On the left hand side, we have 4 minus 4 plus 6. On the right hand side, we have 10 minus 4. 4 minus 4 plus 6 is 6. And 10 minus 4 is 6. So therefore, 6 equals 10 minus 4. We have two examples here. We want to make x the subject, so we need to move y to the other side of the equal sign. We've got a minus y, so we need a positive, so we need to add a y. So minus y plus y, we add the y to the other side to balance the equation. The two y's cancel each other out on the left hand side, and we're left with x equals z plus y. And again, you can check it out. You can put the numbers in. The first equation was 8 minus 2 equals 6. In the rearranged version, we've got 8 equals 6 plus 2. In the next one, we've got A equals B times C. So we want to get B by itself. C is being multiplied. The opposite of that is division. So on the right hand side, we'll divide B times C by C. What we do on one side, we've got to do on the other side. So we'll divide A by C as well. On the right hand side, the two C's cancel out, and it leaves us with the formula A divided by C equals B. And again, if you put the numbers in, you can see it all works out. Here we've got x equals y divided by z. We want to get y by itself, so we need to move z to the left hand side of the equal sign. Opposite of division is multiplication, so we'll times y by z. What we do to one side, we do to the other, so we'll times x by z as well. And it leaves us with the formula x times z equals y. And again, the numbers all work out. So let's get back to our wheel and see how we can get all these formulas from these two triangles here. So we have our formula V equals I times R, but we want to know what current is. So we need to get current by itself. And as we've seen, we divide both sides of the equal sign by R. Otherwise the equation will become unbalanced. So we have the formula V divided by R equals I times R divided by resistance. On the right hand side, the resistances will cancel out, and you're left with the formula V divided by R equals I, and you can swap it round to I equals V times R. You can see what happens if you don't balance the equation. I'll put some numbers in. Voltage 230, I 23, resistance 10. And you can see 230 equals 230. 23 times 10, 230. Now if we just worked on the right hand side, we divided the resistance by the resistance, you'll see that we end up with 230 equals 23. Obviously not. So it's important that what you do on one side you do on the other. We balance the equation. We divided everything on the right hand side by resistance, or 10 in this case. So we need to do the same to the left hand side. We end up with 230 divided by 10 equals 230 times 10 divided by 10. There's no need to have all that information on the right hand side. The two 10's cancel out, and so we're left with the equation 230 divided by 10 equals 23. V divided by R equals I. This time we've got resistance equals voltage divided by current. We want to get voltage by itself, so we need to move the I to the other side of the equal sign. This is a division. Opposite of a division is multiplication. So this time we times voltage by current, and to balance the equation we've also got to times the resistance by current. On the right hand side the current cancels out and you're left with the formula V equals I times R. Again, we can check it out with the maths. Resistance 10 equals voltage divided by current. 10 equals 10. If we don't balance the equation, we get 10 equals 230. Balancing both sides, we end up with 230 equals 230. And our final formula, 10 times 23 equals the voltage, 230. Right, let's bring a square root into it. We have the formula I equals the square root of power divided by resistance. The numbers would be 23 equals 5290, that's your power, 5290 watts, divided by resistance 10. The square root of 5290 divided by 10 is 23. Now we want to isolate and get power by itself. So first off, let's just get rid of the square root. So what you do to one side, you do to the other. So we'll square both sides. And when you square the square root, it cancels it out. So you're left with the formula I squared equals P divided by R. And we can check that out, see if we're still all balanced. I squared is 529. And on the other side, 5290 divided by 10 equals 529. So we're all good so far. Now we wanted to get power by itself, didn't we? So to get rid of this R on the bottom, what we need to do is times it. Opposite of division is multiplication. So we'll times by R on the right hand side. On the left hand side, to balance it, we need to times by R as well. Right hand side, the R's cancel out. And we're left with the formula I squared times R equals P. And you can see the maths all work out. 529 I squared times 10 resistance equals the power, 5290. That would be watts. So squaring a square root cancels it out. As you can see here, the square root of 5290 divided by 10 equals 23. Now if we square that, it now equals 529, which is 5290 divided by 10. So the square root and the square cancel it out. Last time we wanted to find power by itself. This time we want to find resistance. There's an extra step here. Let's have a look. So as before, we square both sides. In doing so, it cancels the square root on the right hand side. And we squared the I. Now we want to get resistance by itself. But it's so much easier when you're transposing equations to get this R onto the top line. So let's do that first. It's a division, so we multiply. And what we do on the right hand side, we do on the left hand side. So we've got R times I squared equals P times R divided by R. Those R's cancel out and we're left with R times I squared equals P. Now we want resistance, don't we? By itself. This time we need to cancel out the I squared. We can move the whole I squared and that's a multiplication. So the opposite of multiplication is division. R times I squared divided by I squared equals P divided by I squared. What we've done to one side, we do to the other. The I squareds cancel out and we're left with the formula P divided by I squared equals R. And you can look down here if you want to at the maths at each stage and you'll see that it all works out. We're always keeping it balanced. Once you get more confident at doing your transposition, you don't always need to do the maths along with it. If we had the formula voltage equals the square root of power times resistance and we wanted to isolate the power, again we square both sides. Voltage squared equals the square root of power times resistance squared. The squaring of the square root cancels it out. And we're left with the formula V squared equals P times R. Again we want power by itself. So we divide both sides by R. And that leaves us with the formula V squared divided by R equals P. So power equals the voltage squared divided by the resistance. With transposition, it's just repetition that builds your confidence. So let's do another one. Slightly different. We've got resistance equals voltage squared divided by power. Now we just want voltage by itself. If we don't want voltage squared, we want voltage. As I mentioned before though, you got something on the bottom line, get that up the top first. Just makes life easier. So it's a division. We want to get voltage by itself. So we times both sides by P. That cancels out the P on the right hand side. And we've got P times R on the left hand side. So we've got P times R equals V squared. Now we want to get voltage by itself. To get rid of the square, we square root. What you do on one side, you do on the other. So we square root both sides. That'll cancel the square on the right hand side of the equation. And we're left with the formula, the square root of P times R equals V. And you can flip that over if you like it that way. The V equals the square root of P times R. Sometimes you might not have the values that you need. Say in the power formula, power equals voltage times amps. You might not know what the voltage is. But in the Ohm's law triangle, we know that voltage equals current times resistance. So therefore, we can put a bit of that into the power triangle. So we take out the voltage and replace it with I times R, because I times R equals V. Current times resistance equals the voltage. So we get the formula P equals I times R times I. Now there's two I's in there. I times I is squaring itself. So we can simplify that formula to P equals I squared R. Here we have power equals current times voltage. And looking at the wheel, current is derived from voltage divided by resistance. We could put that into the formula, drop out the I, put voltage divided by resistance into the formula, and then we get the new formula, power equals voltage squared divided by resistance. So there's another formula from the wheel. Here's another one. If we have the formula resistance equals voltage divided by current, we know from the power triangle we get voltage from power divided by current. And so we can remove the voltage from the formula and put in power divided by current. We have two currents, so they're squared. So we end up with the formula resistance equals power divided by current squared. Right, okay, let's start looking at some practical formulas that we are going to use. An important formula is the adiabatic equation and the thermal withstand. These formulas help us confirm that our CPC and our live conductors are correctly sized. Let's have a quick look at the reg. It tells us that for a fault of a very short duration, K squared S squared shall be greater than the value of the let-through energy, I squared T, of the protective device. So we're doing two things here. We're checking that the protective device will operate in such a time before the live conductors reach their limiting temperature. And we're also confirming that the size of the CPC is adequate to carry that fault current. Let's have a look how we can transpose these different formulas. So we've got I squared T equals S squared K squared. This one's quite straightforward really. We want to get T by itself, so we need to get rid of the I squared. I squared is multiplying, opposite of multiplication is division. So we divide both sides of the formula by I squared. The I squareds on the left hand side cancel each other out. And we're left with the formula T equals S squared K squared over I squared, your thermal withstand formula. So to get from the thermal withstand to the adiabatic, we want to get S by itself. S is the size of the conductor. So first off, let's get rid of the I squareds on the right hand side. The I squared is dividing, so we need to times. We do that on both sides. So we end up with I squared T equals S squared K squared. Let's get rid of the squares. We'll square root both sides, and we'll end up with the square root of I squared T equals SK. And we're still looking to get S by itself, so we need to get rid of the K's on the right hand side. The K is multiplying, so we divide both sides by K, and we end up with the formula the square root of I squared T over K equals S. And we can rearrange that to the familiar S equals the square root of I squared T over K. But hang on, the I squared, the square hasn't been cancelled. It's still written in the formula, but if you actually work it out, what we're actually square rooting is just the time, because the square root cancels out the square. Let's have a look at another handy formula. This one is for the resistance of a cable. In books like the on-site guide, we get tables with the value of milliohms per metre for common conductor sizes. If you know what 1 metre of copper conductor's resistance is, we can work out what it is for longer runs. So in this example here, we've got 40 metres of 10mm squared copper conductor, 10mm squared, milliohms per metre of 1.83. The resistance of that cable is 1.83 times 40 divided by 1000. That's to get it from milliohms to ohms. So the resistance of that conductor is 0.0732. But imagine if we didn't know the length. All we had was the resistance, and it would be handy. Say this was a bonding conductor, and we had a resistance of 0.073. You'd be able to calculate how long that bonding conductor actually is. So we can transpose this formula to work out the length, and that can be really handy. The length of a bonding conductor, how much cable you've got left on a reel. So let's transpose for length. The original formula was resistance equals milliohms per metre times length divided by 1000. We should be getting the idea of this by now. So let's get rid of the 1000 first. The 1000 is dividing, so we multiply. We multiply both sides. We get the formula 1000 times resistance equals milliohms per metre times length. And the thousands cancel out, don't they? We want to get length by itself, so let's get rid of the milliohms per metre. The milliohms per metre is a multiplication, so let's divide that. We divide both sides by the milliohms per metre, and they cancel out on the right hand side. And we're left with the formula 1000 times R divided by milliohms per metre equals length. So imagine if you had a job that required 2.5mm squared twin and earth, and you thought you might need about 25 metres. You've got a reel of cable in the back of your van. You're thinking, oh, do I need to buy a new reel of cable? Well, I've got enough here. We can do an end-to-end resistance test and work out how much cable's on the reel. 2.5mm squared twin and earth, the live conductors have a milliohms per metre of 7.41. And so connecting our meter probes onto each end of the live conductor, for example, the 2.5mm squared conductor, we take a reading, end-to-end resistance, and we get 0.28 ohms. We put that through the formula, 1000 times 0.28 divided by 7.41, and it gives us a length of 37 metres. So it might save you a trip to the wholesalers. You got enough cable on that drum. If you had a brand new reel of cable, 100 metres say, the resistance reading you'd be expecting would be 0.74. So that's quite useful. And you can also use this when you're fault finding. It's possible that you might be able to find a location of an earth fault, or any short really, on a conductor by using this method as well. Imagine if a nail's gone through a conductor. This could have happened some time ago, but it's only starting to show as a fault now. You might have installed an RCBO or something. But you think, what's happening? We've got a short circuit. The neutral earth loop has been shortened by the nail through the cable, and this will make an RCD trip all day long. Now if you're fortunate and the stars align, you take a resistance reading, it'll be an RN plus R2 in this case, and the milliohms per metre for the live and CPC connection is 19.51 milliohms. Again, we do the resistance reading, seeing if you can measure this shortened loop, and say we get 0.12 ohms. We can put that through the formula. We'll get a length of 6.15 metres. Now this might give you the clue to where the problem is. So you measure about 6 metres from where you're testing from. You might have to lift a board or even open the wall up. And sometimes it works and you find the fault using your meter and a bit of knowledge to find a hidden fault. And it does work. You might not have the milliohms per metre values to hand though. So you can actually work out the resistance of a cable from the resistivity formula. So the resistance formula is resistance equals ρ times L divided by cross-sectional area. Rho is the resistivity of copper. We're using copper in this example. All metals have got different values. In copper, we're talking about tiny numbers here. In copper is 1.71 times 10 to the minus 8. If you can remember 1.71 times 10 to the minus 8, you times that by your length and by the cross-sectional area of your conductor, and you'll get a value of resistance. Say I've done 2.5 millimeter squared cable here, and for the 2.5 millimeter squared cable, 35 meters, it works out it's 0.24 ohms resistance for that length of cable. From 1.5, it's 0.40. So if you're doing your R1 plus R2, that would be 0.64. And we can compare it to the milliohms per meter values, and they're there or thereabouts. The differences are tiny. I got 0.26 for 2.5, 7.41 milliohms per meter, and 0.42. With numbers so small like this, you're always going to lose a little bit in the maths. You can see that this works out. Using the resistivity formula gives you the same values as the milliohms per meter. Using the resistivity formula can be really useful. We can transform this formula to find out the cross-sectional area of a cable, which can be useful if you're not sure sometimes. Sometimes you might have a shower circuit. You're not sure if it's 6 mil or 10 mil. It used to happen a few years back where they used to use 16 millimeter squared twin and earth from a switch fuse to a fuse board. Don't do that anymore, but it was done. And sometimes this 16 millimeter squared twin and earth had a 6 millimeter squared CPC. The older version had a 10 millimeter squared CPC. It's good to know which size it is, isn't it? If you're doing an inspection, it's good to know if it's got a 6 mil or a 10 mil CPC, so you can do your adiabatic. It's good to transpose this formula to work out the cross-sectional area of a conductor. Now let's go through the transposition again. Should be getting there now. Resistance equals rho L over A. So we want to get the A by itself. We need it on the left-hand side of the equal sign. A is dividing, so we'll times both sides by A, and we end up with R times A equals rho L. We want to get the A by itself, so we want to get rid of the R. R is timesing, so we divide both sides. Cancels out the R on the left-hand side, and we're left with the formula A equals rho L over R. A is our cross-sectional area. And I've got an example of getting the cross-sectional area here. We've got the 1.71 times 10 to the minus 8 times 35 meters divided by 0.239. The 0.239 is the resistance reading we took. I put it at 0.24 here. I just rounded it up. And if we put it through the calculator, we get 2.5 millimeter squared. Brilliant. Don't forget this is 0.239 times 10 to the minus 6 to get to the right values. So let's go back to that 16 millimeter squared twin and earth cable. We weren't sure if it had a 6 mil or a 10 mil CPC. A couple of ways you can test it. You could do an R1 plus R2 and work it out that way. You could do like a wonder lead, so you can do like an end to end. So you're just testing the CPC. That's what I've done here in this theoretical example. And after I've nulled out my leads and everything, I get a resistance of 0.06 ohms. I've worked out, I think it's about a 35 meter run. And so I put the numbers to the calculator and I get 9.97 times 10 to the minus 6. 0.06 times 10 to the minus 6, I get 9.97. Which is suggesting, under this set of circumstances, the CPC is 10 mil. It's only going to be a suggestion because it's going to be really difficult to know the length and stuff, but then you can transpose the formula around to get the length. But that's the beauty of transposition. You do a transposition to get the length. If you want to know the resistance, you can do the transposition to get the resistance. Cross-sectional area, you do a transposition to get the cross-sectional area. That's why it's a really useful skill to have. A bit of basic transposition knowledge. And this video has been basic knowledge. Maths can get tricky, it's not my best subject, but I hope I've explained everything clearly and correctly. Let me know if I haven't, and I hope you found it useful. And as always, thanks very much for watching.